Good morning, everybody. Thanks for joining today. John Handler. We're going to talk about best practices in using Amazon Elasticsearch service. We have a number of different topic areas to cover, and we're going to look at designing and architecting, managing data, deploying a domain, sizing a domain, testing your domain, stabilizing your deployment, securing it, hardening it, and then hosting multiple workloads within that domain. So it's a really broad set of content that we're going to cover, and really look forward to getting into it with you. For those of you that are new to Elasticsearch and Amazon Elasticsearch service, Elasticsearch is a database technology that primarily came to the fore as a search engine. You put your data into Elasticsearch, send your queries, and Elasticsearch provides you with relevant results for those queries. As it was out there and as it grew, people started using it to flow log data. You send your application logs, your infrastructure logs, security logs, all of those to Elasticsearch. And then Elasticsearch, in tandem with another open source technology called Kibana, allows you to build visualizations, dashboards on top of that data to see how your infrastructure is performing, see how your application is performing, maintain your security stance, etc. Elasticsearch can be a bit tricky to maintain and to keep the lights on, to keep it operating. So with Amazon Elasticsearch service, we do all of that operational work to deliver Elasticsearch to you in the AWS cloud with minimal amount of operational and other effort on your part. To make the point, Elasticsearch is a database technology. It behaves a lot like a database. On the input side, depending whether you're doing search or logs, you're going to format your data as JSON, send it to Elasticsearch via REST API. Elasticsearch works entirely via REST APIs, or you're going to format your application data as JSON and send that into Elasticsearch as well. Elasticsearch then will index all of the fields in your JSON to provide fielded search on that data. So again, you've already translated it into JSON. Elasticsearch is indexing the fields in your JSON to allow you to search against them. Then on the query side, again, you use REST APIs, and you can send queries to Elasticsearch that are either free text queries. They could also be string matching queries, numeric queries, dates, geographical locations, all kinds of ways that you can query your data. And much like any other database, you would retrieve a result set that contains responses for your query. Under the covers, Elasticsearch is a distributed system, and we have a number of different nodes for Elasticsearch. We have data nodes, which hold your data, respond to queries, and do the indexing for your data. We have master nodes, which orchestrate the cluster and keep the cluster functioning as a whole. And then we have ultra-warm nodes that are higher density storage provided by S3 that provide you the ability to store long tail data at a much reduced cost. We have a number of different security features. We have identity and access management that allows you to gate access to the cluster. We have Open Distro for Elasticsearch security plugin, providing you with fine-grained access control. And then we have integrations with other services. On the input side, we have Kinesis Data Firehose delivering to Amazon Elasticsearch service for your logs workloads, database migration service that can deliver database data to Elasticsearch for search, and CloudWatch Logs that supports a Lambda-backed delivery to Elasticsearch. On the output side, we send metrics to CloudWatch and audit data to CloudTrail. So when you use Amazon Elasticsearch service, you deploy what we call a domain. You use a configuration API that's going to tell us what you want to deploy, and then we go and deploy all of this hardware and software on your behalf as a Amazon Elasticsearch service domain. So digging into our topic areas, the first topic that I wanted to address was designing it and what's it good for. As we already covered, there are two primary workloads for Elasticsearch. First of those is a search workload. And at a high level, what you're doing is you're loading in your data and you're searching it. Elasticsearch is going to give you a ranked set of results based on either matching the text in your queries, matching the strings that you send in, bounding with geo boxes, providing date and other range searches. Ultimately, you can adjust that ranking, but you'll get a ranked set of responses for your query. The second workload, analytics workloads. Some of the characteristics here, you get near real-time availability of your log data for your visualizations, your dashboards, and your other monitoring technologies that are going to be watching what's going on with your infrastructure and your application. So when we're designing for Amazon Elasticsearch service, and when we're trying to figure out the architecture and where it fits in an overall architecture, we have different ways that we approach it for search and log analytics. Looking at search workloads, the key concept here is that Elasticsearch functioning as a database is going to hand you back what you put in. The core entity in the search engine in Elasticsearch is called the document. Document is the JSON object that you create from your source data. It's what you're searching for, and it's what you retrieve. If you think about a use case like an e-commerce use case where you're searching a product catalog, each product in that catalog then would be a single document. And when you design your search workload, you think first about what is it that I want to pull out. For that e-commerce workload, I want to pull out products that presumably and hopefully my customers are going to want to buy. So that's what I would need to put into Elasticsearch. Then I'm going to want a script that walks my database and bootstraps that data into Elasticsearch. You're going to reuse that script. That's a good script to have, because if you're doing dev and test, if you're doing QA, if you need to reload your data or reindex your data for any reason, having that script in ready to go enables you to build out additional Elasticsearch domains, or again, reindex into the current domain. Another really good thing to do is to maintain a canned copy of your data set as Elasticsearch documents in a separate store. Again, that just shortens the time where if you have to reload that data for some reason, or you want to use it for dev and test, you have a quick way to take that data and push it back into a different Amazon ES domain so that you can do dev and test on it. You want to be careful in both search and actually log workloads to buffer your high velocity updates. We'll see in a moment in the interaction over the architecture, you're going to be potentially sending updates from your front ends to the documents in Elasticsearch. Again, taking the e-commerce as an example, if you have customers that are providing ratings or in other ways sending data in, and you need to modify the data in the search index, you generally would do that at the point where they make that modification. But you want to be careful with Elasticsearch that you buffer your updates and you use the bulk API, which we'll get to in a second. Switching over to analytics workloads, again, buffering is a key concept here. Elasticsearch has a limit on the amount of concurrency that it's going to handle. Not a hard limit, it's a soft limit that is based on the hardware that you deploy in your domain, your data nodes and your master nodes. Your data nodes. So we're gonna buffer so that we reduce the amount of concurrent connections that we need to maintain to the cluster. In both cases, that's a really important practice, is to do that buffering. For analytics workloads, actually for search workloads too, but we need to transform the data from its original source form. For search data, it's in some database somewhere. And for analytics workloads, these are log lines. They need to be translated into JSON. The two common methods that we see for that are transforming that data with Lambda and or with Logstash. Logstash is another open source technology that is a streaming ETL on top of your data that can put it into JSON format and can do a lot of sort of modifications or changes to that data as it's flowing through the pipeline. Always use the bulk API, as I mentioned before. Bulk API is a way to send batches of data. You don't generally want to send single documents because, again, concurrency will kill you. We find that there's generally a 3 to 5 megabyte best optimum point in terms of the batches of data that you're sending. And then Elasticsearch includes an ingest processor pipeline that allows you actually to do transform within the domain itself. We generally don't recommend that you use these ingest processors. That puts an additional load onto the data nodes, and generally want to stay away from those. In terms of what you don't want to do, Elasticsearch is not a good durable store. It is not designed for durability. It's designed for low latency, high throughput querying of your data. So Elasticsearch generally should not be your primary store, and you should be using it in tandem with another store that has a more durable storage of your data. It's okay as a key value store. Some of the APIs don't perform as well as a key value as other key value stores would, but you can use it as a key value store. And the last don't is the more data you pull out of Elasticsearch, the heavier weight the workload is on the clusters. So you really want to limit how much data you pull out of Elasticsearch. In other words, don't retrieve large result sets. So let's see how Elasticsearch sits within an overall architecture. For a search workload, the primary and usual pattern is to use Elasticsearch in tandem with another database. The second database is going to serve as your primary store. Actually, it's kind of your first database. That serves as your primary store of your data. You're moving that data from that primary store to eventually Elasticsearch to enable rich searching. So we have a little straw man architecture here. We have a distribution layer and a page rendering layer, then an application layer with business logic, and then our database layer. And within the database layer, you can see, I'm imagining in this case that your main catalog, your source of truth, is going to be an RDS kind of instance, whether it's Postgres or SQL or any of the others. That's going to contain your catalog data. And then you may have also DynamoDB that's going to contain higher velocity data, things like user ratings or clicks or likes, things like that. All of that data you're going to flow down into Elasticsearch, either via a set of scripts, basically, or change data capture from Dynamo to send that off to Elasticsearch to create the index where Elasticsearch is providing you the search over the data that's in the other stores. When we look at architecting with logs, we have some high-level steps that we have to go through, and we have a lot of different means of implementing those steps, but it's important to understand the overall set of tasks that we're doing. So we have a number of data producers. Typically, these are servers, or this is your application logs. So these are, instances of your application running somewhere. You need something to collect that data off of the servers where it's generated. There are a number of different options and ways to do that. That collection layer is gonna forward to a buffering and an aggregation level. So what we're looking at with collect is we want to bring all of the data from these possibly many sources into a central pipeline that is going to allow you to build batches and deliver those to Elasticsearch. Of course, we have a transform step. Again, the log data itself starts out as string lines of data. We're going to transform that, and then we're going to deliver to Amazon Elasticsearch service. Ultimately, we're going to use the data in Elasticsearch service for analysis and reporting. Another pathway that we want to explore here is our collection layer can simultaneously deliver to S3 as permanent cold storage. Generally, you may want to keep your data for longer than you need to have it in Elasticsearch, in which case S3 is a good backing store because it enables using things like Athena or Redshift or EMR to do longer term analytics on top of that data. As we look at some implementations of this architecture, one way that we can implement this pipeline, we can send log files themselves into S3, and S3 will generate an event that we can trigger a Lambda. That Lambda can consume that file directly, transform it into JSON, each log line transform that into JSON and deliver a batch to Elasticsearch service. This is not the lowest latency way to go, but it is a cost-effective way to go. And it also provides you with that permanent storage as part of the pipeline itself. Another option that we have is to use technology like Redis that can serve as a buffer. In this case, Redis is not actually acting as a cache so much as it is buffering the data that's coming out of the EC2 instances. On EC2, we're using Elastic Beats. These are open source log shippers that can deliver those log lines directly to Elasticache. Coming out of Elasticache, then we're using Logstash, which can pull the data from Redis and then transform it and deliver it to Elasticsearch service. We also have a number of managed services that deliver streaming technologies. In many cases, those are the best way to deliver data to Elasticsearch service. We have our EC2 instance, again, where we're running our application, and maybe we're collecting metrics there themselves. There are lots of ways we can get data off of that instance. We have our Kinesis agent, we have our Beats, we have Logstash itself, we have FluentBit, we have FluentD, lots of different ways to get data off of that instance and or containers that are running on that instance. Those technologies, those can deliver to various technologies. And again, this is really more at scale. We're looking at large scale delivery of tons of data when we get into these streaming technologies. Kafka is a very common choice. EMR with Spark Streaming, another common choice. And then we also have Kinesis. Both data streams and Firehose, data Firehose are good choices for streaming that data onto the next path. Depending on which of those you pick, then Logstash potentially can pull from Kafka, and Lambda can pull from any of these technologies. If you're using Amazon Kinesis Data Firehose, that will deliver directly to Amazon Elasticsearch service with a transformed Lambda that's called inline as your data is flowing through. The last one to talk about is FluentD and FluentBit. We can use those for container solutions, along with potentially another beat called Metric Beat that's doing low-level infrastructure monitoring for the instances that are running the containers. All of that log data then can get passed off directly to Amazon Elasticsearch service, or more properly, if you have a larger deployment, you're going to, again, use some aggregation layer that's going to sit in between Metric Beat and or FluentD and the delivery to Elasticsearch service. So we have our data coming into Amazon Elasticsearch service, and we're going to talk about how that data lives in Amazon Elasticsearch service. Within the service, you create indexes, or within Elasticsearch, you create an index, and that is the repository for your data. That index organizes all of the information that you're going to search against, right? So if you think of it as a database table, you won't be far off from the reality. It is something like a table. And within that, if you think of your JSON documents, each document would be like a row in a database table. And each field in your JSON would be like a column. All of that is going to come in, and in the logs use case, you're going to build an index per time period. And this is for data lifecycle management. Most of the tools that you use, Logstash, Lambda, you'll have to implement it, but Logstash will automatically roll over indexes on a day boundary, and you can also configure that. So for streaming information, log data, you're going to create a single index per day. At the end of the day, then you're going to visit the oldest index, potentially back it up, and then delete that index off of the cluster. For search, we're really dealing with one index, and lifecycle management here is more at the individual CRUD operation, right? So when we do Elasticsearch for logs, we're managing indexes by time period and rolling that data off. When we do it for search, it's really managing it at the single index level with CRUD operations. So each index is comprised of shards. You create the shard count when you create the index, and generally speaking, you can't change that shard count. Shards are just partitions of your data, right? So if I choose to have 5 shards then in my index, then 1/5 of my data is going to go into each of those shards. We'll see downstream, Elasticsearch is then going to deploy those shards to particular instances, and that's how we get the compute applied to our workload. So shard is a really core concept. It's important to understand how you do your sharding controls how your data is distributed across the cluster of instances and really creates the performance of what the cluster can do. In log analytics, we generally have a life cycle that looks like sending data to Elasticsearch, right? So we're creating those daily indexes. They're going to live in a hot tier. These are the data nodes that we referred to originally in the architecture diagram for Elasticsearch service. They'll be indexed in that hot tier, and that hot tier will provide them with fast access, will provide us with fast access to that underlying data. As I said, we're going to manage the life cycle of that data by potentially moving that data into our ultra warm tier for longer term, lower cost storage. Other possibilities, sometimes you're going to snapshot that data and back it up and then delete it. But eventually you're going to delete that data off of the cluster entirely. And that is the high performance way to remove data from Elasticsearch is to delete an index. Individual document deletes don't perform quite as well. So for log analytics, we're going to manage our data lifecycle at the index level by moving it, by creating it, and then ultimately moving it to UltraWarm, and then ultimately deleting it. In Amazon Elasticsearch Service, we have an index state management facility that allows you to specify different states that your index is going to live in and move that index across the life cycle that I just talked about. So you create a JSON policy that you're going to apply to the index. That JSON policy is going to specify a set of states and a set of transitions for those states. With this one, you start out in the default state, it's in the hot tier, it transitions to the warm state after 7 days, and then it is in the warm state, it migrates to ultra warm, and you will transition to the delete state after 90 days. So you can use ISM to manage your indexes. We have a lot of different actions that you can perform via ISM. You can snapshot off your indexes, you can rotate them through to UltraWarm, you can delete them. You can use ISM and manage the life cycle of log data that way. Moving down a layer into the deployment and how you should think about deploying the instances that are in your Amazon ES domain. As I said before, and this is really a key point in terms of deployment and sizing, Elasticsearch ultimately is going to distribute the shards in all of your indexes to the data nodes in the cluster. When you send requests, you're accessing a particular index for that request, and Elasticsearch will distribute the request to all of the shards in that index. Each shard will then process the request as appropriate and will serve up the response. Whether it's query, it'll serve a response. If it's an update, it will update its local copy of the index. So how many shards you have, how many nodes you have is the critical way that your workload is distributed across your compute and storage and networking and other resources. So it's really important to understand about shards. We're going to get to that, but we're going to first talk about the different node types that we support in Amazon Elasticsearch Service. So we have a set of instances that includes the M5, R5, and i3 instances. For the larger workloads and for most production workloads, we find R5 to be our best performing, usually most cost-effective instance to use. R5 has a current gen CPU, that CPU tends to be a little bit faster than the i3. It has RAM, additional RAM over the M5 that makes searches run more quickly. The i3 is a more search-aligned instance, and it's a peer for the R5. So it's a hard call between R5 and i3. What i3 has that benefits you is it has an on-instance NVMe SSD, which gives you fast access to disk. In most cases, and especially for log analytics, Elasticsearch is sparing of its disk usage. So R5 is a reasonable choice for log analytics. When you run a search workload, you tend to do a little bit more disk access, and the penalty for using an a network-backed storer can actually grow to be, grow to push you into the i3 where you don't have to pay that price. The M5s are really a general purpose, good place to start. They're a lower cost alternative that lets you kind of get in and experiment. We have plenty of customers that run production workloads on M5s. It's not wrong, but R5s for the highest performance. For the dedicated master nodes are orchestrators, right? They're single-threaded. In other words, out of the eligible nodes for dedicated master nodes, only one of those nodes gets elected as the cluster master. And in order to scale them, you need to scale vertically, right? So we're going to use the configuration in terms of the indexing that you're doing as a proxy for how big you should scale your master nodes. And again, we have here a proxy in terms of the data nodes, in terms of the shard count, right? So out to 10 data nodes, C5 large. We do favor the C5 instances for dedicated master nodes, out to the really large cluster size at the 75 plus data nodes. And you'll see we scale linearly, vertically, C5 large, C5 extra large, C5 2 extra large. And then at the top end, we'd go R5 4x large. Our final type of node is the ultra-warm node. Ultra-warm nodes use S3 as a backing store. They enable you to store a much longer tail of data for a longer term analysis of the log data that you're sending in. You can run the same interactive log analytics and visualization. The access patterns for the data are the same. You don't have to access ultra-warm differently than you access your data in your hot nodes. You simply send the same queries. You build the same Kibana visualizations. Ultra-warm really just gives you large cost savings up to 90% at a trade-off of some latency. So we find that with ultra-warm, our expectation is that you would run for data that has been cached locally within the ultra-warm tier, you can run as hot as fast. That is millisecond response times. As we have to use S3 more and pull data in, you'd start to see that climb into the potentially single-digit seconds. And if you get way out into the large scale, you're storing a petabyte of data in there, it can take up to minutes. So ultra-warm is great. The one caveat, the one qualifier is that ultra-warm is read-only data. So it's not appropriate for search workloads, but it's great for log analytics where basically you're writing your data once and you want to store that data for a much longer time period. So let's get into the topic of sizing of clusters. And I'm coming back to the main point here. Again, the shards are the workers in the cluster. So when we do sizing, we're going to think about not only the shard count, but in terms of the storage that they use, but also the shard count in terms of the CPUs that they use, right? We're going to map these shards onto the resources that are on the instances to generate an amount based of an instance type and an instance count based on the storage needed and based on the CPU needed. So The configuration that you're setting in terms of the data node count is what's going to determine the capacity of the cluster, right? Each data node is going to provide you a certain amount of CPU, certain amount of storage, networking, and RAM. So all of those are going to be the key components, key resources that Elasticsearch is going to use to process your requests. We have a number of different knobs that you can turn. So your instance type will determine the core storage and CPU counts. The instance count allows you to increase your parallelism and deploy your workload across more than one instance. The storage available is a baseline where when you're indexing all of this data, it gets stored in the cluster as indexes. So you have to provide enough storage in order to store your indexes. And then last is the shard count. You adjust your shard count to align with your instance count and your instance type so that you don't overwhelm that instance with work. In the main, log workloads are storage driven. So when we deploy an Amazon Elasticsearch service domain that's going to be working with log data, it tends to be that the instance type that you need to support the amount of storage that you need for your log data already has plenty of CPU for the new data that's coming in. That's because most of the data in a log workload is actually passive. You are most frequently accessing the newest data, and your access to older data tails off very quickly. In contrast, search workloads are more driven by CPU and JVM. Search workloads tend to be read, log workloads are write, and so they have different characteristics when we're looking at scaling. It's not uncommon in a search workload to need a lot more CPU than you actually need storage. We'll go through how you figure it out. So the first thing we're going to do is think about how much storage we need. We're going to base this on the amount of source data that we're sending in. It's a little bit different for logs and search. For logs, again, we're maintaining this rolling set of indexes, and we're going to need to store all of that data on the cluster. For search, we just have that single index, and we're still going to need to store that data on the cluster. So to figure out the storage needed, we're going to start with the source, and potentially for logs, the amount of source per day. Then when Elasticsearch takes in that data, it's going to create an index out of it. The index data structure is not the same as the source data. Typically, it's about 10% larger. So we're going to add a 1.1 factor in the equation. That's the inflation between the source data and the index data. Now with Amazon Elasticsearch service, you generally are going to use a replica. Actually, it's a best practice to use a replica for redundancy of data in the cluster. Each replica is a full copy of the set of data that you've sent in. So each replica is going to be a factor in this equation. If I use one replica, I have to multiply the amount of storage I'm using by 2. So that's the factor of 2 in this equation. For a log analytics workload, then I have some notion I'm going to retain this data for a certain number of days. 7 is a common number in terms of the overall retention of this data. For search, we can simply set this to 1. There's only one copy, there's only 1 day's worth, if you will, of data. We're going to retain that data for 7 days, so we would use 7 as a multiplier. And then lastly, we have to make sure that we're not sizing our disks exactly to what our storage need is. We need overhead, so we're going to add an additional 15% overhead. Just running the numbers, if I have 100 gigabytes of search data, then that would use approximately 250 gigabytes of storage. For logs, if I have a terabyte of source data daily, then that needs about 18 terabytes of storage with 7 days of retention. Once we have these baseline numbers, and again, this is more relevant in terms of logs where you're generally storing more than you're processing, that's going to give us a lower bound on the instances that we can deploy based on the storage that those instances supply. Now we want to figure out the shard count. So we're going to create these indexes and we're going to set our primary shard. we already have an estimate from the prior screen of what the index size will be. It's going to be the source size times 1.1. So when we set the shard count, then we're going to divide the total index size by the target shard size. We have different target shard sizes for logs and search. In a logs workload, we're going to want to go out to a maximum of 50 gigabytes. Generally, that means targeting somewhere in the range of 45 gigabytes. That gives you a little bit of headroom as you're growing to add more information before you have to change your shard count. For search, we really want to look at somewhere in the 20 to 30 gigabyte range for the shard size, the target shard size. So we just run this, we just divide the index size by the shard size. That gives us a shard count for this index. And then especially for log analytics, we're going to use a template. That template will get applied every time a new index is created. And it allows us to set the number of shards and the number of replicas for every new index without having to do it manually, right? So we're going to put this template, we're going to say it applies to every index that starts with the prefix logs. And we're going to apply settings to that, which is the number of shards are 50 and the number of replicas is 1. And finally, and especially more for the logs use case, we need to adjust for the usage. So we want to set the CPU count in the cluster. In other words, we want to deploy nodes providing vCPUs that are 1.5 times the active shards. So what is an active shard? Well, for a search workload, when I'm querying and indexing, every shard is actually involved in the indexing, and n shards, where n is the primary shard count, are involved in queries. Those are all active. Okay, so generally we take the larger of those two. For a search workload, we would say the total shard count, the primaries and the replicas, is the number of active shards. For log analytics, by and large, unless you have a workload that really is going to go back in time a lot, they are dominated by writes to today's index. So if we look at today's index and the primary and replica shard count total, that will tell us how many shards are active. We're going to want CPUs in the cluster that are 1.5 times the number of shards that are active. So for example, if I have 4 data streams going into 4 indexes in a cluster, let's say I have syslogs, I have Apache web logs, maybe I have my application logs, and maybe I have some instance statistics in terms of CPU usage, RAM usage, what have you, going into a 4th index. So I have 4 indexes. Let's say each of those indexes has 5 primary shards and 1 replica. So each index has 10 total shards, and each of those 4 indexes is concurrently active. Those are active indexes. So I have 40 active shards that total. So we want to make sure that we have, in this case, a total of 60, or 64 is a round number, total vCPUs in this cluster. All of this is really nice and a good way to start out with sizing and capacity planning. But with Elasticsearch, it's fairly difficult to predict how it's going to behave, because Elasticsearch's performance is very tied to the actual workload that you're driving. And so the first thing is, we always want to test. You want to plan for testing as part of your development cycle. You want to test out your particular workload with your data to understand the performance characteristics of Elasticsearch. And then even in production, even when we've already launched, we need to monitor and adjust as we go. So we're constantly with Elasticsearch monitoring and figuring out how we're going to adjust the deployment to meet the needs of the workload. It's very important, again, during development that you plan for and execute testing of the workload to lock in the optimal configuration in terms of the nodes and the nodes that you're using to process your workload, their instance, their type, and their count. As I said before, the performance of Elasticsearch is hard to predict. it's highly dependent on the particular workload that you're driving into Elasticsearch. And it's not really an exact science. Like, we do our best. I gave you some general guidelines and things that will get you to a good starting point in terms of where you're going to go with this, with your cluster. But in order to figure out exactly sort of an optimal deployment, you really need to run testing. And I have a couple of ideas for you around testing. The first of those is that you really want to use your actual data and your queries, if at all possible. Because you can use simulated test data, and that will give you some answer, again, directionally correct, but really to dial it in, you have to be able to test with your actual data, your actual mapping, your actual queries, so that you get the actual usage that you're going to have, right? Another common thing that I see is people send 5 or 6 different queries over and over and over again. We need to have at least thousands and better millions of distinct queries and updates to really measure the workload. It's important that you're not, if you're doing simulated data, it's important that you don't actually generate a lot of queries that send you 0 results. That's unrealistic, unless that's how your workload actually is. You want to be careful that your queries are generating results that are more or less like the results that you're expecting to get. So as a test plan, one way to approach this is to look at a single shard on a single instance with a single index. And you're going to take that single shard and you're going to drive your workload to it and measure the error-free throughput across variations in the shard size. So this is going to help us dial in what is the optimal shard size for your workload. You can vary the shard size, if you have enough data, by increasing out to that 50 gigabytes for logs or 20 to 30 gigabytes for search. Actually, you can go to 50 for search as well, to vary that shard size and find out where you get the best throughput. Once you understand your optimum shard size, then you want to understand your optimum shard density. So this is more than one shard, still a single index, still a single instance and index, and you're going to keep increasing your data size in multiples of the optimal shard size and deploy additional primary shards to identify what is the error-free throughput, what's the best throughput that you get at any particular shard count. You will then know what's my best shard size, what's my best shard count per node, and then you can scale your shard and node count for your full workload based on those numbers. Finally, you want to deploy your full workload, test it and monitor it, especially paying attention to the CPU usage, the JVM usage, and the queues internal to Elasticsearch that we surface under the search and write thread pool in your CloudWatch metrics. You want to monitor those to make sure that your requests are not queuing or not being rejected. So we have a couple of ways that we can stabilize and harden our deployment. The thing that we really want to do and look at is skew. So this is a very common issue that we see in a lot of clusters, and it's really important to avoid if at all possible. If I'm hosting multiple different indexes, and those indexes are different sizes, and especially if the shards in those indexes are different sizes, then I end up with an uneven deployment of my data across the nodes in my cluster. And it's really important that you balance out especially the shard sizes is what we use as a proxy. So you want to try to create your indexes in such a way that all of the shards for that index and all of the shards for all of the indexes on the cluster are actually roughly the same size. Ideally, they would have the same usage as well. And shard size is kind of a proxy for usage. It's a little bit harder to get your arms around usage, but sizing you can definitely do. So one of the ways that you can equalize these different index sizes is to use the rollover API. Rollover is a facility that Elasticsearch provides that allows you to specify an end condition for an index that's not a time window. It is, in this case, could be a size or a document count. When your index hits that particular size, the rollover API will then roll it to a new index. So that's a really good way to equalize different index sizes. You trade off the ability to manage your data very closely according to the time window when it was generated. If I have very tiny index data for one index and I'm trying to get it out to 50 gigabytes, it might take me a month, in which case I can't delete that data after a single day. Second thing you want to do is, or second way of equalizing things, is to vary your retention windows. So you can still manage it on a time basis. I can still have a daily index for my large indexes, and then I can have maybe a weekly index or a monthly index for my smaller indexes. Ultimately, if you have very different resource usage for different workloads, it's pretty important to move the larger workloads onto their own domain. Like ultimately, you'll do better trying to scale 2 orders of magnitude different workload by putting it into its own domain that you can scale independently of lots of your little guys. So you want to evaluate that as well. Let's talk about securing your Amazon ES domain. We have a fairly complex security model now that's developed over the years that offers you various layers and places that you can apply security to the traffic that's coming to your cluster. If you are using a logs workload and you're using Kibana, we have a Cognito integration that allows you to bring in your federated identity provider information into Cognito, that allows your users to sign in via Cognito in the Kibana UI, and provides credentialing in terms of IAM roles for those users based on their login and based on your Cognito identity pools and user pools. That IAM credential, that role, then comes to the domain. With Amazon Elasticsearch Service, you can choose to put you communicate with your domain over an endpoint. That's just a DNS entry where you send your REST commands. You can choose to have that endpoint at a public IP address or at an IP address within your VPC. Our best practice is to use your VPC private endpoint. So with that, you can then control the access to the endpoint using security groups, EC2 security groups. Assuming that you send your traffic through the security group, then IAM is potentially, if your traffic carries a role with it, IAM is going to check that role against permissions that are put onto the domain. Each domain carries its own IAM resource policy. You're going to use that policy to control who has access based on their IAM role. Once traffic gets into the domain, we have our fine-grained access control provided by our Open Distro for Elasticsearch security plugin. You can set up based on the Cognito role, or you can use basic HTTP auth, username, password auth. Internally, the Open Distro plugin manages a database of users for the basic auth, and you also can map these IAM roles onto those users. The security plugin has a suite of permissions that allow you to control access to indices, access to performing actions that are more administrative in nature, and allows you to go down to the field level for access control. We also provide TLS, so secure transit between nodes within the cluster. You can enable that at domain creation. And we provide integration with AWS Key Management Service for encrypting your data at rest. Whether it's a particular instance store, whether it's EBS or on-instance storage, for ultra-warm nodes if it's S3, for your snapshots that are also in S3, all of that data you can encrypt with your own key. As I said, using a VPC endpoint is the best practice way for Amazon Elasticsearch Service. Amazon Elasticsearch Service actually deploys the software and hardware for your domain into a service-managed VPC. This is not within your own VPC. It is a service-managed VPC. When you use a VPC endpoint for Amazon Elasticsearch Service, we're going to deploy Elastic Network interfaces into the subnet and security group that you specify when you create the domain. So that is how you gate the access with the security groups around those ENIs. And then you could, if you're already sending traffic from within your own VPC, you can gate access that way. It's a little bit more complex when you have Kibana access. Kibana has to reach to these endpoints. One way is if you have the Amazon Elasticsearch Service domain endpoints in your public subnet of your VPC. In other words, if there's public access to that portion of your VPC, then your Kibana traffic can go through, and you can use either IAM or Open Distro Security to provide access control for the cluster itself. If you're placing your Amazon Elasticsearch Service endpoints into your private subnet, then it becomes a little bit more complex. Generally, we see customers using either some kind of bastion in the public subnet that is allowed to talk to the private subnet and allowed to send traffic forward. Another way that customers solve this is to use VPN for that bastion inside the public subnet. So either bastion, proxy is another way that people solve this problem too. A couple of thoughts about making your cluster more durable. Within the service, we provide 3AZ replication for your domain. This is just a checkbox. This is a best practice. You should use 3 zones. For maximum durability, you should use 2 replicas, not 1 replica. However, each replica is going to drive your storage up, and that potentially is a cost. So you want to weigh whether the additional replica will bring you benefit for that additional cost. It does give you, if you use 2 replicas in 3 zones, then you can survive loss of either 1 or 2 zones and still retain all the data in your domain. You can also survive the loss of 1 or 2 nodes in the cluster without being in danger of losing any data from the cluster. So we generally see customers using 1 replica across 3 zones, but you should know that the more durable solution would be to use 2 replicas. We divide the nodes evenly across the zones, and then the data is replicated across the zones. So we ensure that Elasticsearch has a copy, a primary or replica for each of the shards go into each of these zones. If we're looking at a more DR kind of scenario and strategy, we don't have currently in the service any kind of data replication. So the strategy for building a hot or warm standby is to do a dual write. And depending on how you're ingesting your data into Elasticsearch Service, there are lots of different ways that you can intervene to split your data out. I'm visualizing one for you here where we're taking Kinesis data stream that's receiving all of the traffic from the Kinesis agent or the beats or what have you. We're executing a Lambda that's going to deliver to 2 different Kinesis data fire hoses, one in each in one of 2 regions, and then deliver to Amazon Elasticsearch Service. This way we have a hot standby. We could use it, or a warm standby. We could use it as a hot standby as well. Obviously, this level of redundancy is going to drive a lot of cost, and you have to evaluate, the criticality of the workload. Do I need to maintain this workload no matter what? In which case, having a warm standby or a hot standby is going to provide extra value and extra durability for disaster recovery. We wanted to cover some of the alarms, and we surfaced about 40 different CloudWatch metrics. If we look at them in sort of stacked or priority order, then we want to look at just a few of them. Your cluster status is red, yellow, green. Green is obviously good. Yellow means that some shards somewhere are not yet allocated, or it can be a very transient state as you get towards everything allocated. Red means data is not allocated everywhere. Some data may have been lost in the cluster. Anyway, it's unavailable right now, and that's a condition you should monitor for. You should monitor your free storage space, and your index writes will be blocked when you run out of storage. So I have both free storage space and index writes blocked here. You need to monitor those to understand that you've run out of storage. For free storage space, you really want to keep about 25% of the total as free space. Your CPUs and your JVM are important indicators of how your workload is running. You want to keep your average CPU to be less than 80%. Usually 60% is a pretty good target. And you want to keep your JVMs less than 80%. Elasticsearch garbage collects at 75%. So if it ever gets up to 80%, something is going south. The only other one I'll mention here is the queue depth and rejected executions. As I mentioned before, Elasticsearch has internal queues that it's using to manage the request stream. And those queues ideally would be empty. If your average queue size across all of your nodes exceeds 100, that means you have 100 items queued. Your actual queue depth per node is 200, so you're starting to get into a yellow area. If you run out of queue space, then you get rejected executions. You want to monitor for that. Last thing I want to talk about is tenancy. So tenancy is a pretty broad topic that covers a lot of different implementations and a lot of ways that you need to look at your cluster. So at a high level, a tenant in your cluster is an index. It's a workload, right? You can choose to co-locate multiple data streams into a single index and have a multi-tenant index. You can choose to take multiple data streams and deploy each of them to an index. And then finally, if you have enough data and enough usage that you're driving, you can actually deploy multiple data streams across multiple Amazon ES domains. So this is an example that I'm pulling where the tenant here, this is from NBC Sports Engine. There's a link there. They gave a talk with us at reInvent in 2018. They manage youth sports leagues. They have about 20,000 youth sports leagues in their system, and they wanted search across all of those. So each of those sports leagues then serves as a tenant. And the question was, how do we best deploy this? Do we do 20,000 indexes? Well, no. Your shard count ultimately is going to be way too high, and it's going to be really hard to support that workload. Okay, so shall we put all the tenants into one index? Well, probably, except some of those tenants are driving much higher usage than others. In that case, what you want to adopt is a hybrid approach. You're going to put the small workloads into a single index. Tenant, 2 through n here will go into a single index. And then the larger tenants, you're going to move out into their own index. At the high end, if those tenants get really, the usage gets really heavy from them, you're actually going to split them out into their own domain. So in order to manage this, the best practice and the best way to manage this is to maintain a mapping of tenants to domains and indexes in a separate database. This allows you to always pick up the tenant location before sending any request. It gives you the flexibility to add some flags that would, say, disable the write status of an index. That allows you actually to re-index that tenant's data somewhere else and move that tenant. Either it's a different index or it's a different cluster. Your front ends and all the rest of your application don't have to know about the underlying location of those tenants. And then finally, when we get to the really high end, we recently launched support for cross-cluster search. What this lets you do is it lets you join multiple clusters, and those clusters you can send a query that spans across multiple Amazon ES domains. When we have very, very large workloads that are decomposable in the sense that the data itself, you can localize some sub-portion of that data, then you can put that into a single domain, and then you can pod it out across multiple domains. And then with cross-cluster, you're able to query across the whole data set, even though you can scale each of the sub-pieces independently. And a couple of benefits here: it minimizes your blast radius, and it does allow you to scale independently. So just wrapping up, we looked at a number of different areas and brought out some best practices in those. We have our design goals. We have the ways that you architect and build Elasticsearch service into your overall architecture. We talked about data lifecycle and how you manage data within Elasticsearch itself. We talked about deploying which instance types, what are the different instance jobs and how you should use them, sizing your domain, the importance of testing, how to stabilize and secure your domain, how to harden for the long haul, and finally, how to host multiple indexes and multiple tenants within a single workload. Thank you very much for your time and attention. Really appreciate it today.